All right, quiz 7 solution. Two infinitely long grounded metal plates at x equals 0, x equals a. They are kept at zero potential. And the ones at y equals b and y equals minus b, their potential are v0 and minus v0 as shown. Now, the configuration is independent of z. This is the solution we can write based on separation of variables. Now we are asked to apply the boundary conditions to show that we can write the solution as vxy equals to sum n equals 1 to infinity, a n sinh k n y sine of k n x, and we are asked to determine k n and a n. Okay. So the first boundary condition is v equals 0 at x equals 0, right? So then I'm going to write v0y is equal to, and the y part, we don't have to worry about that in this case, c sine of 0 plus d cosine of 0. Now, this is going to go away. This is 1. So what this tells us, okay, given that the y part is in general non-zero, d must be equal to 0. So that's the first one. So the solution becomes vxy equals to a e to the ky plus b e to the minus ky sine of kx. Now, I don't worry about the c because you can just factor them in, and then this is basically a redefinition of a and b. Okay, second, v equals 0 at x equals a. So I'm going to write v a y equals to, again, the y part, a e to the ky might be, and then this one will be sine ka, and that's equal to 0, right? So again, the y part in general is non-zero, so sine of ka must be equal to 0, and this has multiple solutions. Ka should be n pi, where n is 1, 2, 3, etc. Okay, we don't write negative ones because in the original solutions, if k is negative, then you have a problem, right? So we assumed k is positive to start with, and that's what we have here. So this is what it is. So I determined basically kn, n pi over a in this case. So part of the problem asks us to determine kn and an. Okay, so that's the second boundary condition. The third boundary condition gives v equals v0, and then the fourth boundary condition, v equals minus v0 at y equals minus b. So y equals b, v equals v0. So let's write that. V of x b, which is going to be a e to the kb plus b e to the minus kb sine of kx. And again, k is here, right? So we know that. That's the first one. Okay, then that's equal to plus v0. Well, I have two unknowns here, a and b. So I got to use the other boundary condition, vx minus b. Then I would have a e to the minus kb plus b e to the plus kb, because if this is minus, the minus ky, right? And then this is going to be sine kx equals to negative b0. Okay, one thing we notice here is these are one negative of the other, right? So this is the same, sine kx. So that means this part needs to be negative of this part, right? So if you just equate them with a negative sign, that's what you get. So a e to the kb plus b e to the minus kb should be equal to negative of a e to the minus kb plus b e to the kb. Okay, so if it is minus of this, what you notice is that a e to the kb should be equal to minus bk to the eb, or from the other term, you have the same thing, b e to the minus kb equal to minus a e to the minus kb, which gives me b equals minus a. Okay, so if you put these together, I think you pretty much get this second equation. So let's show that. We have vxy equals a e to the ky minus e to the minus ky. Okay, I replaced b with negative a, right? Sine of kx. That's what I have. Well, if we use the definition of sinh function, we can redefine this a, because e to the minus ky minus e to the minus ky, I can replace this with sine hyperbolic of ky. Right? So now, if this is a solution, k, remember, is n pi over a. So for n, k is n dependent, and there's infinitely many solutions, and their linear combinations will also be a solution. So that's the justification. So we can write n equals 1 to infinity an. Okay, linear combinations means there's infinitely many a coefficients as well. Sine hyperbolic kn y and sine of knx, where kn is given by n pi over a. So that takes care of it. Now, the only thing remaining here is determining an. Okay, and that's use the Fourier trick to determine an, right? So in this case, what I'm going to do is, okay, I can multiply, okay, I'm going to use the same boundary conditions I used here at B, one of them, right? So we have xb, I can write as v0. It's going to give me n 1 to infinity an sine hyperbolic kn b sine knx. Now you multiply both sides by sine kn prime x and then integrate. Okay, so sine kn prime x v0. Okay, now I'm going to integrate dx, and on the right hand side, when n equals n prime, that's the only one that will survive. So I have a n prime sinh kn prime b, and then I have the integration again of the square of this, right? Sine square kn prime x dx. So x equals 0 to a and x equals 0 to a. So if we integrate that here, we will get a over 2. So, and we just need to integrate this part to get the result. So an, let's turn every an prime to an. So an a over 2 sine hyperbolic of kn b equals to v naught. If you take the integral of this, it's going to be minus cosine of kn x over kn, evaluated 0 to a. Right. So let's do it. This is going to be an a over 2, kn is n pi over a, sine hyperbolic of n pi b over a. And then on the right hand side, I have v naught over, okay, kn is, we already took care of it, minus v naught cosine of n pi a over a minus cosine of 0. Okay, so this is cosine n pi minus cosine 0. This is 1, but cosine n pi, if n equals 0, it's going to be give you positive 1. If n equals, okay, if n equals 0, it's positive 1. N equals 1, cosine pi is negative 1. So it's going to be minus 1 to the power n. Okay. Odd powers, it's going to give you negative, and even powers, it's going to give you positive. Okay. So minus 1 to the power n minus 1, and there's another minus 1 here. So let's put them all together. So if n is even, then minus 1 to the n minus 1 will be 0. 1 plus 1 is 1. So there is no solution for n even. So n is odd, then minus 1 to the n minus 1 will give me minus 2. Another minus here, so it's going to be 2v0. So then an becomes, these a's cancel. This is 2, another 2 here, 4v0 divided by n pi sine hyperbolic n pi b over a. Okay, that completes the solution.